Okay, so really what I'm going to cover in the next 45 minutes and probably will take us some time in the next class, which is something called the statics review. And some of you may wonder why do you need to review with us statics? I said, you guys, in my class here, you should, it's a must, not a choice. You should be able to take a beam, put some loads, and tell me, okay, what is the bending moment? What is the shear force? And so on. Why is that? Because if you remember what I discussed in my last class, I said in the flow chart of the design process, we need to estimate the loads, put the loads on the structure, see how the structure would react, like what is the deflection, what is the moment, and then we take the moment and we size our member to be able to safely resist the bending moment. So I guess from this discussion, you believe no other choice. When we say design, it means we need to know about statics and get those things like reactions and shear force and bending moment, those things you have learned in the last year. Okay, and as I said, I know probably this last year and too far I cannot remember. Don't worry about it. You will see. I'm going to give you really a good and quick, good and quick reminder and refresher of statics analysis. Okay. Now, really, what I want to start is here reminding you of what do we call this thing in the left. So when it comes to structural systems, which we discussed on brief last class, we talked about trusses and we talked about frames and arches and verandile. Now, anybody to turn on the mic and tell me what do we call the picture on the left?
Shear force diagram.
Yeah, thank you. This is, yeah, you're true. If I'm gonna point out, so this one here is the shear force diagram. But really, my question was okay about. Sorry, I have to be specific. What do we call this thing in terms of structural system? Is it truss, frame, arch, verandile, or something else?
It looks like frame.
So you're thinking that this is a frame?
It could
Okay,
be a
beam.
Okay.
frame. It could be a cantilever beam.
Joist or a beam.
Okay, beam.
Okay,
Yeah,
so
okay, beam.
whoever, thank you so much. For sake of time, probably have to cut it you a little bit. Sorry for that. But yes, you guys, if you said that this is a beam, you're true, you're correct. If you said your joist, you're true, correct. Okay. However, we always, because from the beams, there are kind of a subcategory of beams. We would like to be more specific, and this is what's called simple beam. Okay, because there are some other types of beam which will come next. So, guys, what you see on the left is simple beam. When we say simple beam, it means it's one span. It means only two support, and there is no overhang. Okay. How about the one on the right? Again, uh, what do we call this thing on the right? Okay.
Cantilever.
Overhang beam.
So it's correct. So what you see on the right is a simple beam from here to there. It's a simple beam, very similar to one on the left. However, we have a cantilever or overhang from both sides. Okay. So guys, you can see it's very simple. I want to remind you quickly on how do we find the shear and the bending moment for the one on the left. So that's very simple. I'm gonna, probably type in the equations. So this number here, the moment it's happening in the middle, and remember that the load acting is called uniform load. So what you see on the simple beam to the left is something we call it uniform load. Look at the units. It is 5 kN per meter. It means every linear meter of this beam will see, or it's under the effect of 5 kN. Okay. So this called, typically it's referred as W, like uniform load, and the relationship between the moment or the maximum moment and the load and the span is as follows. M equals W multiplied by L squared, and then divided. I'm sorry, I don't know how to do that in BGF in a good way. However, this is what you're supposed to read. So it's L squared probably need to move it this way. So you take the span, you square the span, you multiply the span squared by the uniform load, you divide by 8. Look at this. So this will give you the bending moment here, which is the maximum bending moment. Okay? Any moment away from the center is less, because this is a parabola with the maximum in the middle of your beam. That's bending moment. Very simple. Okay? Now so this is called bending moment. 0 at the support, 0 bending moment at the support. How about the one on the top? It's called shear force diagram. Shear force diagram. And again, I would like you to do it manually for you. Guys, where did we get the 40? It's very simple. W is 5. So it's here. So this is your W. It is 5. And then where is my span? My span is here, which is 8 meter. So how to find the 40 is simply 5, which is the load, multiplied by 8 to the power 2, then multiply by 8, and you will get 40. Okay, next is my shear force. So the shear force diagram, it looks like a triangle with a 0 value in the middle. So the shear value at the center of your beam is equal to 0, and maximum at the support, maximum shear at the support. And simply, I'm going to give you the equation. So the equation for the shear at the support is equal to W multiplied by L divided by 2. And again, not very difficult, not super science, because simply the total gravity load affecting the beam, very simple. The total gravity load is simply 5 times 8, because every meter is 5, and we have 8 meter. So 5 times 8, that's 40. And remember, we have to support, and it's symmetrical. It means half of the load will go to the right support, half of the load will go to the left support. So 40 divided by 2, you will get 20 kilonewton, which is simply the reaction and the shear force affecting this beam. Okay. So let's move. So this is something I want every one of you to know. If you have a simple beam that has uniform load, so the maximum bending moment is WL squared over 8, and the shear force maximum is W multiplied by L divided by 2, which is the same shear and the reaction on the same time. Now, when it comes to, I have a simple beam that we have 2 overhangs. We have a simple beam and we have 2 overhangs. So in this case, it's kind of a very similar, but your parabola will be hanged not from the 0, will be hanged from the moment at the cantilever. So I mean, guys, please, for now, can you please, when you try to think about this one, that's how I personally do it. I want to find the moment here. I'm going to show you where I'm trying to find the moment here on top of the support. And simply to find this bending moment, what you have to do is you take this 5, which is the load per linear meter, you multiply times 2, which is the length of the cantilever. So if you type the uniform load times the length, so simply you're replacing, in a way, you're replacing your load by equivalent load, which is simply in the middle, okay? Just like that. So here is your load acting here. How much is this one? Very simple. It is 5 times 2. So this one will be simply 10. I'm going to write it for you guys here. So this will be 10. Okay, 10 kilonewton. 10, which is a point load, 10 kilonewton. And then this force here, it simply completely replaces the uniform load on the cantilever. Now you take this 10, you multiply by the lever arm. The lever arm is simply from where it acts to the point that you estimate the moment, which is, remember, because this is simply replacing the uniform load, it means it's in the middle. So if this is 2 meter, it means 1 and 1. So 1 times 10, it means the moment on top of your support here is simply 10 kilonewton meter. And this is something you see here, okay? So this is your moment at the support, okay? Guess what? I'm going to show you something. I'm not sure if you know that. If I connect a point from here to there, if I connect a point from here to there, okay? And so you can see, because of the symmetry, we have 10 on this side, 10 on this side. Guess what? The WL squared over 8, which is 40, you simply hang it from here. Okay, so from the middle here, you go up, okay, and simply this will be your 40. So from here to there, simply it is WL squared over 8, which is 40 from the left picture. And because you already have 10 on one side, so your moment will be only 30. And again, there are so many ways. I don't know how did you learn this one last year, but this is how I do it myself. You still have the parabola, but the parabola is not hanging from 0. The parabola is hanging from -10, and that's where you get the 30. When you think about the shear force, again, at the tip of the cantilever, the shear force is 0. And then after the slope of this line, is simply 5 kilonewton per meter. So every time you go 1 meter, you go down by 5. So after 1 meter, we're 5. After 2 meters, we're 10. So the shear is equal to 10. And then you're hit by reaction. So guys, when you think about this reaction, is simply you take the entire length of your beam. So 8 plus 2 plus 2. So this will give you 12 meter. And then if you multiply 12 meter times 5, you want to see what is the total force going down. What is the total force going down? So 5 times 12, you get 60. And because it's symmetric and we have 2 supports, so every support, the reaction will be 30. So my reaction here, which is this number here, is your reaction, and this is your reaction. Now what happened is your reaction will push the shear from -10 to +20, and it goes with the same slope. So those lines, this line and this line, they are parallel, and the slope is equal to the load. So it goes down to the 0 and it's mirror. Okay. And again, if you learn this different way, again, I have my own school where I learn and I know how to do things, but probably your teacher or your instructor in the first year taught you differently. Okay. Doesn't matter for me, as long as you know how to estimate and find the bending moment and the shear on a simple beam, and a simple beam with overhang, I'm okay with that, no matter what's your method. Okay. Now, you can see here, the loads could be different. So the load not necessarily has to be a uniform load. It can be a point load, or it can be uniform load, or it can be triangular load, and your beam can be cantilever, can be simple beam. So the next picture on my document here, it gives you a table, and this table, you know what's very popular table. You will see any concrete or structural design, you will see it has this table. It's kind of a design aid, and instead of you doing things manually, it tells you exactly what is the moment on a very quick basis. Really, please focus those. So I'm going to focus on this one. So this one is very important for me, which is how to find the moment and the shear for assembly supported beam. I don't know if this is right, because I don't know if the resolution is bad, but the maximum bending moment is simply, oh, I'm sorry, because look, you have to be careful, because look at the definition. So in this equation, they use W capital. And what is W capital? W capital is the total load on your beam, which is WL. I was about to say that this is supposed to read WL squared. However, it is right the same way, because simply W here is W capital, not like what I did, because look at the left side, W capital, which is total load, equal to the uniform load per meter multiplied by the span. Anyway, so this is how you estimate the bending moment and the shear for simply supported. Also, please focus for this one, which is how you find the shear and the bending moment for a cantilever. I'm sorry, a cantilever beam. So this is a cantilever beam, and probably shortly I'm going to tell you the difference between a cantilever and assembly supported, but please focus for those. Something also I want you to be careful and know and understand is the type of the support. So the support in structures, they are different. Not all of them, they are the same. Okay, so I'm going to give you here a sketch, and then I'm going to give you a kind of a real live picture. So here in this sketch, you see 3 different types of support. Let me give you a quick question. Okay, question for you guys. Okay, so guys, I'm going to point out to every support, and if you can tell me what do we call this support?
Hinge.
Thank you so much. Yes, this is a hinge, okay? And before I go to other support, let's watch what's happening here. So this support here, it's simply a restraint. Support, it means restrain. It restrains this point of the structure from movement in two direction, which is the Y direction and X direction. We call it hinge, like the hinge of your door. Huh? So if you look at your door, the hinge, your door can rotate, but it doesn't go in anywhere. So the hinge stops this from movement in X direction, Y direction. However, it does not stop rotation. So your beam can still rotate and deflect this way. Okay, next but not jelly, please. Okay, roller. Oh, I said it. Oh my God. Okay, so guys, look at this one. So this support here, we call it roller. And so the roller is simply, look at the name, it rolls. It means it restrains your structure only in one direction, which is in this picture, it is the Y direction. So your beam cannot move up and down. However, if it's allowed, it can move left and right. So X is permitted, but Y is not permitted. Okay, next is, I guess, guys, the answer is here on the slide. Sometimes the answer is on the slide, but I'm not paying attention. So this here, it is the third support, the third, which was fixed. So this one is a fixed support. And we say, when we say fixed, it means the three are not permitted. It means it doesn't go, it cannot move in the X direction. It cannot move in the Y direction. And also the rotation is not permitted. Those are very schematic, and maybe some of you really at this point of time doesn't know what do you mean. So in real structure, how do you look like? Let's go to next step, and then let's look at structure in real life or support in real life. Okay, so the picture here on the left, this picture here on the left, top left, this one here is kind of is a support for sure. It's not concrete. This discussion is not really limited to concrete. It's this discussion applies to any material. So what you see here is a roller support. Okay, and even the one on the right, I know that it's not very close, but this one still is a roller support. And the way we use roller support it's very handy. Okay, it's very handy because simply if you have a roller, it means you're permitting the structure to move. Okay, I'm going to show you maybe an arrow. So the structure can move this way or the opposite. So it can move this way or the other way. And guys, why this is so handy and it's preferred? Because of the thermal effects. Okay, because of the temperature. This bridge is outside, and I will see huge temperature difference between the morning and the night, between the summer and winter, which means the structure is wanting to expand or shrink. And if you restrain the movement in the X direction, here we go. You have so big problem. Okay, you just have to make it roller, and then you have to do something on the top for the joint. Okay. Okay, let's move on to another kind of support. You can see this one is interior. There is a steel column, and this steel column is simply connected to a concrete, probably, I would call it a pier or something below or pedestal. Okay, now let me ask you, what do you think about this one? Is it fixed? Is it roller? Is it hinged?
Hinge.
Wait, please, because this is for a mark. Okay, so please, I'm going to go to MS and raise your hand if you know the answer. Okay, so I have two. I'm going to go with the TOIP.
Hinge.
Hinge. Thank you so much. Okay, so really, this one is a hinge because you can see there is a bolt going in the middle, and this bolt, does it stop rotation? No, it doesn't. It simply, it can rotate. The column can rotate, but since we have a bolt, there is no X motion, there is no Y motion, and it's a hinge. Thank you so much. The next one is tricky, and let me give it to a TOIP a mark. Thank you so much. Okay. Okay. The next one is for 2 marks. The next one is for 2 marks. This, guys, this picture here, because it's tricky, it's not easy. This one here on the right, what do you think? Is this one a hinge, a fix, a roller. Let's see. We have, I think on the top of the list, we have Siham. So let's go with Siham, see what she can give us.
That one is a fixed connection.
Okay. Okay, I'll keep this in mind, okay?
Okay.
I'm gonna get some others. Please, Jared. Jared, what do you think?
I was gonna say fixed as well.
Okay, so Jared and Siham, they are fixed. Okay, let's go with the next one. Brody?
I was gonna say fixed, but now it's starting to seem like it's a hinge.
If you change your input, please, you will have to tell me why did you do that? What makes you change from fixed to hinge?
Well, looking at it, it doesn't look like it's actually inside of the post. It's just on the outside, so it looks like it's just supported, I guess, only in the two directions, not in terms of a moment.
Okay, thank you, sir. Okay, so I have here Brody, okay, and I had Siham, and I had Jared. Okay, I'm gonna take more. I'm gonna take more. So next is I need Mahdi.
It's a fixed and hinge connection.
No, there's nothing
You
called
can't?
fixed and hinged. There's
Well,
nothing. It's one or the
is
other.
it because-
There's nothing called both.
Okay, well, is it because there's a little gap between the post and the actual sorry, I'm having a brain fart here. The joist and the post, right?
Yes.
Just because there's a gap, it gives it a little bit of room to like move or like for like a bend type.
You mean rotate? You mean rotate? Rotate.
Rotate.
Rotate. Okay. Next is, I'm sorry. Next is after Mahdi, you have Domenico.
I'm gonna say moment connection. Or
Moment connection.
maybe I'm thinking
Okay,
wrong.
let's see next. Okay, so Domenico. I need Hamid.
It's a semi-rigid connection, therefore it allows a moment, and that makes it a hinge connection.
You know what? You're making things very interesting and very complicated. And probably have to give you not only one mark. I will have to give you two, not my choice. Okay, let's see. Let's see. Okay, Sunny.
Yeah, I think it's a combination of hinge and the fixed one, because the main bar is hinged with the plate, and the plates are screwed and fixed support with the like another plate. So it's a combination of hinge and fixed both.
Okay. Okay. Okay, guys, thank you so much. I love this discussion. I wish that we can do more of this. Like, you know, Raymond, do you want to say something?
Oh, I was just gonna guess shear connection.
Shear connection. Can you please? I know what you're saying is completely right. I don't want to argue about it or disagree. Yes, it's shear connection, but can you please pick one of roller, hinge, or fixed?
Oh, a hinge.
Okay, guys, let me give you my one penny thing. Okay, now this one here, let's see. I love whoever among you try to understand how this is going to restrain. So obviously 100%, there is no X motion or Y motion, because simply those three bolts. Okay, so those three bolts will simply keep the beam in the same position, X and Y. Okay, however, okay, the bolts, if I put one bolt, place one bolt, so if I cancel this bolt, so I cancel this one, I'm going to do it here. Okay, so if I cancel this bolt and if I cancel this bolt, okay, so if I cancel this bolt and this bolt, The answer here is very simple. Same as the one on the left. If you have only one bolt in the middle, so which means simply this beam, it can rotate, it doesn't go anywhere, which means pure hinge, okay? Those two bolts will make it kind of subjective, because some of you will say, listen, Tahir, those between the two bolts, there is a distance between this one and this one, and this distance will simply have what is something called the lever arm. So there's something called lever arm, which means they potentially have a little bit of resistance for the rotation, okay, because they have some lever arm. And that's why Hamid, it was kind of is the kind of the best theoretical answer. Yes, it is a semi, you know, it's not really fixed or not really hinged, because there is some allowance of rotation, but not 100%. But here is, listen, this is on the book, but in reality, in engineering, the way we do it is, if we connect the flanges, to the column, it means this is a moment connection, because most of the moment or the rotation will come through the flanges. If we connect the web, we do it only shear, and we don't think of it as it restrains the rotation. I know I could be so complicated, but it is exactly what I said, okay? Engineers, they look at this one, they design it as a shear connection, so it means rotation is allowed. However, it is semi allowed, it's not 100%. But by the way, so you know, everyone said something, got a mark already. Thank you. Okay, again, along the same line, you can see this, not the super science here. This one is a hinged support. You can see there is a big pin going through, so this is XY, but no rotation is not is permitted. Sorry, is permitted. Same here, rotation is permitted, but XY is not. Now let's look at this one. What do you think? This one, we will give you some marks. Let's see. Let's look at MS. Okay, we have so far we have 3. So okay, okay. So I'm gonna go with Raymond, and so please tell me if it's fixed or hinged, and why.
It's a fixed one because it can't actually move any single direction, like it's locked in.
But you know, fixed is not about locked in, because this is what hinge does, right? So hinge still doesn't go, but fixed is about rotation. Okay, fixed is about rotation. Okay, so you're still saying that this is fixed or hinge?
I'm still saying it's fixed though, because also with your point, it can't really rotate.
Because of what?
Because all the bolts that are put in.
Only the bolts?
Yeah, that's what I'm just gonna go with that. I'm just gonna say fixed just because of the way the bolts are placed in there.
Okay, only the bolts. You don't see anything in this picture that also will help in preventing rotation. So yes, you're right. I have to tell you the answer right now. So yes, because this bolt and this bolt, they have a lever arm in between. So simply they will stop rotation. But so you know, it's not only about bolts. There are some extra which is not really concrete. Is helping for stopping the column from rotation. Okay, probably guys, this is kind of a little bit complicated, so I'm going to say it for sake of time. What do we call this?
Welded plates.
Those are gusset plates. So those are gusset plates. So the gusset plate are they simply tie your column to the end of your blade, which means they provide also connection to stop the rotation. So it's not only about the anchor bolt, but also it's about those blades that they make this connection as fixed connection. And you're right, this is how it's being done before you pour concrete for the foundation. Okay, excellent. So guys, let me give you here, probably we will do that next class. So please get ready for next class for more on analysis and you know, finding reactions and bending moments. But I want to say something before we probably end today. Guys, you know, the whole structure engineering is built on zeros. Okay, we take zeros and simply we build a whole science on top of them. What are those 3 zeros? Any guess? Zeros. Did you learn last year about zeros?
The summation of forces along x is equals to 0.
Yes, so that's one of the zeros. Okay, so
The summation of all the moments is equals to
let's write
0.
it down. Let's write it down. Sigma, and I don't have, again, I don't have or sum. I don't have a symbol, so I can write symbol, but the sum of x, f in the x direction is equal to 0, if you will. So that's 1 0. Anybody else know Jelly to tell me what's the next 0?
Y.
Who said that?
Mehdi.
Mahdi. Thank you, Mahdi. One more mark. Okay. So sum of f sub y is equal to 0. And so, guys, those stability or equilibrium equation, so far we have 2 only. So those will ensure your structure is not going to move in the x direction because there is a balance of forces in the x direction. And also they make sure that your structure will not move in the y direction because there is a balance in the forces in the y direction. Okay. So now we have 2. What's the last one?
Moment.
So some moment, I'm going to write it in plain English, around any point equal
0.
to 0. And so the third one is as important as the first 2 because simply this one will guarantee that your structure is not going to rotate. Okay? I want to say something also before I develop the idea. I want to say something that what happened is, guys, is let's write this down. Okay? Now, when we design structures, we know, that's a fact, that we build 3D structures. That's a fact. Look at your house, look at any structure around you. All of those structures are 3-dimensional structures. 3-dimensional structures. Okay? However, when we do the analysis of a specific element, we can simplify the analysis by kind of simplifying the 3-dimensional structure into 2-dimensional element. For example, look at this, please. Look at the frame. I'm going to draw a box around this frame here. So this is a frame, which is sometimes we use it for warehouses, or maybe this is called a 3-hinged frame. Hinge. Okay, very popular in structural engineering. 3-hinge frame. When we build a structure, it's not really one of those. It has to be series of those, series perpendicular to your screen, and we simply just create a 3-dimensional structure. But when we analyze the frame, we typically don't analyze in 3D. It's kind of more complicated, and it requires probably computer. And so what we do is we take the 3-dimension structure and we abstract it into 2-dimensional elements. Like, for example, the frame you see. Let me ask you a question for you. Are you guys following this discussion? That structures are 3D, but when we analyze and we try to design elements, we turn them into kind of abstract, a 2D, to simplify things. Are you following? Okay, if you're following, I don't see anybody say no, I don't follow. So I'm gonna assume yes, you're following. Okay, so I'm asking you, those equations are for 2-dimensional analysis or 3-dimensional? Okay, should I write here those like sigma x, sigma forces in the x direction, sigma forces in the y direction, and sigma moment around any point is going to be 0? When I wrote those 3 equations, am I referring to 2-dimensional structures or 3-dimensional structures?
2-dimensional structure.
Okay, thank you. Anybody else has input on this?
2-dimensional.
Okay, let me give you a couple of marks, guys. So here is one for Jelly and there's one for Hamid. I start to kind of remember your voice, okay, which is great. Now I'm connected to you. Okay, now you're right, guys. So this is 2D. What you see here, those are the equilibrium equations if you analyze your structure in 2D, that's what we do mostly. Listen to the word mostly. So mostly, even if we design a house, a warehouse, we take all the elements, abstract them into 2D, and then do the analysis, but we build them in 3D. However, there are some structures we cannot do that. Like some structures, you cannot really abstract them in 2D. And I'm gonna give you an example from Calgary here. Look at the bow. Look at the bow tower. The bow tower is east of downtown. Probably if you are along the 7th Avenue in downtown, you will see it's a very nice kind of curved, looks like a bow, curved surface. And guess what? We cannot. That's not possible. We cannot analyze it as two-dimensional shape because of its shape. So in this case, we need to analyze it in 3D. It's a must. We have to build our model, and we do find the bending moment as if it will be built. Now, here is a very tough question, okay? And this will be for 3 marks. 3 marks, okay? Are you guys ready? So I said here, if you analyze in 2D, just like this frame, we will have equilibrium in X. So Fx is equal to 0, summation, and the summation of the forces in the y direction is equal to 0. And the third one is sigma moment around any point is equal to 0. When we analyze a structure in 3D, not 2D, what do you think? How many equilibrium equations do we have? Is it still 3, or we have more or less, and how many?
4.
4 question.
Okay, wait, guys, wait. Okay, so I need to get this. Okay, so the one who will get the 3 mark is the only one will get the perfect answer, not close. Okay.
For
so
Z-axis.
No, so guys, turn off your mic. I have to call your name, please. So Paulo.
Yeah, so you need forces in your X, Y, and Z directions to be 0, as well as your moments in the X, Y, Z axes to be 0 along any point in the structure.
So how many?
6.
Done. Thank you. You get 3 marks. Guys, we're done. We're done. Thank you. So guys, just like Christian or Paulo said, yes, you're right. You know, if you analyze your structure in 3D, which means, look at this, the forces in the X and Y, because in 3D we have 3 different axes, which is X, Y, and Z. So we simply have 3 balance of forces in X, Y, Z. And also we have 3 rotations, rotation around or moment around X and moment around Y and moment around Z. So when we analyze the structure in 3D, we simply end up with 6 equations, 6 equilibrium equations, which will make things a little bit more complicated. Okay. So you know, I don't know, like, you know, now it's 2:40 and there's only 10 minutes left. So probably I would, you know, let this part here, which is simply in details how to find the reactions and bending moment and shear, to the next class, probably 1 hour. But for now, probably I'm going to accept some questions. So questions, please.
Sir.
Okay, so Shuman. That's funny.
Yeah.
That's funny. Okay, probably, you know what? Here we go. Next class, you are the first one I'm going to ask questions, no matter what's the order, so to give you some marks.
Yeah, I need some.
Okay, so get ready. I think Michael said something at some point. He said, well, the braces, which means that I think he was referring to gossip plates, I guess. Okay, so probably I'll give Michael for another mark, +1.
I'll share it with Ayushman, however you pronounce it. 1.5 each, man. Let's go.
Okay. Okay, guys. Any questions so far? Okay, fantastic. We're done for today.
Sir.
Okay, go ahead.
When it comes to in design and finding the moment, I mean, in the design in general, do we need to show you the diagram of the shear force and the max and the moment diagram, or we can just use those formula that you gave us there and use those formula to get the moments and the shear force?
That's a good question. It's a good question. I kind of never thought about it, but I know the answer for sure. So, when we do the design, we design for the. Okay, let me show you. Probably I'll go here. Okay, so let me go to this. This slide here. Guys, are you following the question? So Jerry is asking. So when we do the design, should we only use this equation, find the maximum bending moment, and simply use the maximum for our design, or we have to draw the diagram? So here is the answer. Are you guys ready? The answer is, if you want to design your beam and not really careful about the material, you don't want to save any amount of material, for sure, go ahead, find the maximum bending moment. So this will give you the maximum at the center, and we will go ahead and design this whole beam. And let's say we have the results will be we need maybe 325 M. And so what we will do is we simply put the rebar all the way from here to there. Okay. And this means, guys, my beam is going to be strong here because it's going to resist the maximum bending moment. But remember, as we go close to the support, what happens? You can see, look at the parabola. The bending moment dies as you go to the support. And what this means? It means the moment here is 40, probably here is 30, 25, 20, 10, 0, okay? So again, hopefully you get the answer. The answer is, if you're not really want to save any amount of money for material, then what you do, you take the maximum bending moment, you design the maximum, and then you simply use the rebar all the way across your beam. However, if you wish to do some saving, what happens is when the moment applied to the beam is reduced, then in this case, maybe what you will do is you will also reduce the rebar. So if you, for example, if your design asks for 525 M, so which means maybe no need to extend those 5 all the way from here to there. Maybe what you'll do is this. Maybe you will do this. Please watch me. So I'm going to put here 3. So this one will be, for example, this one here will be 225 M's. And those will not really go all the way to the support. Okay. And then I have 3 supports, 325 M. Okay. So please watch this, So the section in the middle will have 5 because simply your maximum bending moment needs 5. But as we go to the support, you can see at this section, if I cut section here, I'm asking you, this section here will have how many rebar? This section here will have 3. And why 3? Because the moment here is not really as big as this one. Did I answer your question?
Yeah, I got it. Thank you.
Guys, which means, again, I mean, maybe you're not following. If I am not really, I don't want to save any amount of rebar, then I take the maximum, design for the maximum, put it all the beam. If I want to save my design and save some material, in this case, I'm going to go and see what happens to the moment after some time. And this is illustrated by the parabola. So I get another moment and I kind of try to save on the rebar. So I have to design more than section. So this is time consuming, but you save some money. Okay, guys, we're now 2:50, so our class is over. I'm going to stop the recording and I will see you guys on Wednesday morning. Thank you.